Okay, so from today, I will be taking over the lectures from Professor Chen Yunxun. She has already taught you about the fundamental knowledge of robotics. For example, forward kinematics, backward, inverse kinematics. Today, I want to share some information about path planning of robots. If we want to move a robot starting from an initial position, define a sign, I would like to move that robot to grasp this cup. Of course, I need to know the coordinate of the cup, and then I can use inverse kinematics to figure out what would be the joint angles when I move my robot in this configuration by calculating the angles, right? Once you use this inverse kinematics, you know, okay, that's my final destination. This is my initial one, this is my final one. What you need to do next is to design how you are going to move your robot from the starting point to the end point. You can move like straight, along a straight line, meaning the end effector coordinate follows a straight line. Or there is a curved trajectory. I will tell you what is that curved trajectory. Okay? Eventually, you reach to this position, and then you may have a gripper. Maybe it's electrically actuated or numerically actuated. Either way, you you drive the gripper, perform the grasping, and then you take the second move. Maybe you want to pick up into a different configuration, move it somewhere else, put it down, release the gripper, go back home. So usually it's a sequence of motions. And along this sequence, it's a bunch of move from A to B. Basically, there's an A point, move to B point. You basically define where you want to move from and where you are going to move to from A to B. And you also describe, is it like a straight line or like a curvy line? And there's a reason why people sometimes would like to move along some kind of curvy trajectory. I will tell you today. So let's start with my handwriting. I'm using iPad to teach you, so I will be writing some math and make some drawings. You need to understand my English writing. So this is my handwriting of capitalized characters. They are easy to understand. Sometimes my Z looks like this. Sometimes S looks like this. Sometimes my J looks like this. Yeah, I think the capitalized one is easier. So the small one. So the most difficult one probably is R and S. Okay, that's how I write. Of course, sometimes I write R like this. S, of course, sometimes like this. So if you have difficulty understanding my written character, let me know. Okay? So let's define some symbols. So let's say this is a robot. Okay, I'm not going to draw something professional, just indicating a robot. So let's say this is the end effector. I'm gonna use P point in this lecture. And there are multiple angles. For example, this is like the one, maybe if we define things like this, and so on. And we mostly work on 6 degree of freedom robot. So in today's lecture, I'm gonna use a vector of x to keep all the angles. So these are like my variables. Okay, just for today's lecture. And I'm gonna call this configuration. Because every position a robot stops, you can call this a configuration. Another one, okay? So that configuration is gonna be defined by the collection of joint angles, okay? And P point, you can say it's a three-dimensional point, but in fact you are controlling the coordinate attached to the end effector. So let's say the end effector looks like this. Usually it's like a circular plate. And let's say there is a coordinate. This is the end effector. Okay? So that frame, if you only focus on the XYZ, then I cannot tell the difference if I spin around certain axes. So in fact, you are controlling not only the coordinate of the end effector, you're also controlling its orientation. So in fact, P is like 6 degree of freedom as well. So in this case, let's say I'm gonna use ABC to represent the angles, just for easier description. So it's like a certain angle along certain axis, I call it A, and the second one I call it B, and then it's like a Euler's angle. So if I determine the coordinate by some kind of transformation with respect to the joint angles, this is forward kinematics, right? If I just plug in some kind of transformation with my joint angle in order to determine the coordinate of the end effector, that is forward. So I'm gonna call this transformation F. Okay. If I try to determine the joint angles with some kind of transformation in terms of the end effector, that is the inverse kinematics. Right? So I'm gonna call this I. Okay? So you know, as human, we usually don't care what is the angle of my elbow. I only care about my hands, where my hands are. I don't care about the body. So you can grab this like this way or this way. It doesn't matter. I just want to grasp this cup. So in human design, or humans' way of thinking, we usually design robot trajectory by the end effector, coordinate of the end effector. That's what usually happens. But in fact, in robotic control, you're controlling the motor. Okay, so there's always a lot of transformation between the end effector coordinate and the joint angles. So today, I want to share with you what's the usual way, and later on I will teach you one way to do robotics control in an unusual way, and that was done by my graduate student and myself, and that works pretty nicely. Okay, so let's talk about the usual. So let's say there's one case where we want to move from, since I already use ABC, so I'm gonna say I want to move from a P0 point to some Pn point. Okay, so in the design space, so let's say this is so-called the P0 point. This is the Pn point. If I want to move straight, then in computer, you want the end effector to move straight from P0 to Pn. So you have to tell the computer or the controller where to go to at the middle. So it's like you are making small cuts. Like this one could be P1, this one could be P2, I can call this one P, I'm not using I yet, let me call this Pi. So I'm making n points, actually n plus 1 points, because including the P0. So in total, from the beginning to the end, there are totally n plus 1 points. All I need to do is to calculate inverse kinematics for every n plus 1 points. Why is that? So usually from human, we tell the computer these two. So these two are known information. These are like information from the user. You request the robot to move from a starting point to the end point. So those are given information. So these two are given, right? It's very easy to compute the intermediate point on this straight line. It's easy. It's math, right? So those points at the middle, I can call them intermediate points along the straight trajectory can be computed. Very easily, right? Once you have them, what do you do next? You basically perform inverse kinematics for the configuration at that particular coordinate. So you are computing for the configuration for the I point. And how do you do that? You basically use the inverse transformation. But you need to, what do you need to do? You need to do n minus 1 times in total. Totally. n minus 1 times. Because there are n minus 1 points. So it really depends on how many intermediate points you want to decide. Or if you only choose 3 points. Then you tell the controller to move from a first initial point to a first intermediate point, and then move to a second intermediate point. Let's say there are only 3. After the third one, you directly go to the end point. In that case, the controller doesn't guarantee between each point it's going straight. So if you do not use enough intermediate points, it could be moving like a wavy curve. Okay, because you didn't tell the controller what are the configurations to be assigned between points. So usually for controllers, if you assign a linear motion, it actually cuts this straight line into so many small points and perform a lot of inverse kinematics for each point. So the controller, the computer needs a little time to perform inverse kinematics. Okay? Now, let's think about a different way that could be more effective. So, again, I want to move from P0 to Pn. But in fact, this time, I don't mind if you are not moving straight. Just move the way you like it. As long as you reach at the Pn, I'm okay with it. So a pretty effective way to do it could be like following some kind of curvy trajectory. And I'm gonna tell you what that is. So this is P0, this is Pn, right? What you can do first is to do inverse kinematics. Then you will get the x0. Next, you can perform the same thing for my touch panel. Oh, okay. Sorry. Then you can do the same thing for xn, right? So what are the configurations? They are angles. So this is like a theta 1 at configuration 0 until theta 6 for the 0th configuration. And this is like the theta 1 for the nth configuration. And this is the theta 6 for the nth configuration, right? What you can do next is to focus on specific angle, actually each angle. So let's take a look at, for example, the first angle. What you eventually want to do is to start with theta 1, 0, and ends up with theta 1, n. So what you can truly do is, let's say this is time, and this is the start, and this is the end. Okay, I don't know why this is happening. This is the end, okay? And let's say these are the joint angles. And let's say this is my theta, for example, the j theta at zero configuration. And let's say the J theta at the end is supposed to change to a new angle. I call this theta J comma N. So what you can do is to linearly, I don't know why, come on, the tip of the Apple pen is a little bit ruined. So you can linearly change the joint angle from the initial one and reaches to the last one. You can linearly change it. And you do the same for all 6 angles. So by this way, you realize you don't really need to perform inverse kinematics too many times. You only do it once for the first configuration, and then you do it once for the final one. And then you basically figure out how the motor is gonna move. You have a starting motor angle, and then you end up with a final motor angle. However, at the middle, somewhere at the middle, it's gonna be some combination of all 6 angles, but you have no idea how it looks like. So that's why if you say this is a starting configuration and this is the end, you know the joint angle combination at the start, you know the ones at the end. You ask every motor to rotate linearly from its starting angle to the final angle. What you get at the end is some kind of curvy motion. It's gonna be a curvy motion. And you have no idea where those any vector is gonna be, unless you truly compute for the any vector coordinate at every intermediate configuration, unless you try to compute it. And usually, if you have a computer that is working on simulations, of course, simulator will compute for every n vector position at a lot of intermediate points, so that you can see it, right? But in robots, you don't really need a user interface and show you the trajectory. You just need to say, okay, move from here to here with curvy trajectory, and usually they do this because this is the easiest way. You don't need a lot of inverse kinematics. You guys take homework, right? Inverse kinematics is harder than forward, more complex. Forward kinematics is like plugging in some equation, a bunch of transformation, boom, you get it. But when you solve inverse kinematics, you may have multiple solutions. You need to figure out a way to determine which one is the right one. Okay, it's like solving for unknown parameters. It's more complex. So in this research field, there are people trying to avoid the usage of inverse kinematics, try to use lesser the better. Okay. Now, once you understand about this, I'm gonna talk about obstacle avoidance. If you have an idea, let's say I want to pick up this phone, and the cup now is an obstacle. So if my robot starts from here, and if I ask the robot to move straight toward the phone and pick it up, I will hit the cup. So the assumption is, for robots, you have to know where the obstacle is. Otherwise, it's very dangerous. Because it's a blind robot. It's gonna hit everything the arm swing at. So we usually give the robot its eyes with camera, 3D camera, or a bunch of sensors. So let's consider the problem with known information of the obstacle. Even with known information of the obstacle, if you want to automatically generate a path from the start toward the target without hitting the cup, it's quite troublesome. Of course, there are so many solutions. You can do this, you can do this. There are infinite number of solutions that can reach to the target without hitting the target. There are infinite ones. But for computers, for a practical system, you don't want too many solutions. Just give me one solution. So as a designer, we need to determine what is the most appropriate. So in this research field, there are many algorithms try to find out what is the best trajectory. We don't want to make a large route. Just move closer, make a small route, and then move toward the target. That's usually the best way to do it because you save energy. Think about a robot arm. Whenever you drive the motor to lift the arm, you need electricity. If it's a really heavy robot, you need more power. More power means more electricity. And that's basically cost. So if you can have smaller movement, you reduce your cost. You don't want to own a company, buy a lot of robots, but the robots are moving in the most inefficient way, which wastes a lot of electricity. Eventually, the boss is losing money. So you want the robot to be moving in the most effective way. Okay. Now, today I'm gonna show you something about realizing how safe your robot is. So while you're moving, you are always evaluating how close your robot arm is compared with basically by determining the shortest distance between the robot arm and the obstacle. So if you hit the cup, you're not safe. If you keep away with a distance, then you're safe. Okay, so it's like solving for some kind of trajectory with constant calculation of the shortest distance. Okay? First, I think I need to tell you about how to find the shortest distance between a robot. It's not easy, actually. And it takes time. So, if you have a real robot arm, it doesn't look like a simple figure like what I did here. Okay? It has nice geometry, nice shape. Let me try to draw one. Okay? So usually you have a bottom. Maybe there's a case. So maybe it looks like this. Usually there's a thickness here, and then you have another part. Right? So there's geometry. I'm just trying to, and usually there's another portion here. So there's a motor. There's one motor here, right? There's another motor here that spins in this way. There's another one. There's another one. Right? You have done that. I'm not going to finish all of it. Just ugly and but I want you to understand they are arbitrary shapes. And if I have a robot arm made by manufacturer 1, and then another robot arm made by manufacturer 2, they have different geometrical design. So if you truly want to compute the shortest distance from the obstacle to some part of your body, then you are probably evaluating some arbitrarily shaped geometry and then some arbitrary shaped obstacle. So for example, if I have an obstacle that looks like this, some arbitrary shape. So probably in fact, the closest point is this tip. And then maybe if you do math, if you precisely compute, there is a projection point here. So it's such a precise measurement if you are truly doing this. So numerically, trying to find a pair of points that shows the shortest distance between two geometry takes time. Usually it's actually an optimization process, finding shortest point between two objects. That is never efficient. So in research and also in practice, we will try to simplify the model. And when we simplify the model, we will simplify in such a way so we become safer. We don't simplify it so that we could be becoming less safe. What does it mean? And what does it mean by simplifying? Let's say I want to simplify this geometry into a cylinder. Just the smallest cylinder that is containing the geometry. The smallest possible. And maybe for the obstacle, I will consider it as a point. So maybe there's a point. I just consider it as a point with some radius. As you can see, when I do this, I try to find a simpler geometry, so later on it's easier for me to calculate the shortest distance between a ball and a cylinder. And when I pick up the cylinder and the ball, I try to cover everywhere of the part, but of course I know I am having some gap between the real geometry and the cylinder. So my cylinder is a little bit wider than my true geometry. So it's not precise. However, it's safe. If the ball, doesn't contact with the cylinder, no contact, no collision. If the ball have a tangent contact, like a single point contact with the cylinder, even that happens, it's possible there's no collision because my geometry is inside the ball, my robot arm part is inside the cylinder. There's still a tiny gap. Okay, so as you try to find a good trajectory with safe distance, we're talking about safety, right? It's okay to be safer, but it's not okay to be risky. What is a riskier example? So let's say I have my arms are affecting the same situation. If I have a simplified geometry inside and a simplified ball inside, then when the ball and the cylinder contacts, I already collide. There's already collision. So in this way of, in this field of research, safer than that. So this is safer. And this is less safe. Okay? So we use simplified models. Simplified models. So the next is to figure out how to compute the shortest distance between the ball and the geometry. So what's going to happen is, now I have a simplified cylinder. My arm, I don't know what happened to my arm. I think my arm is okay. Right. Okay, and I have a ball, right? So if the ball and the cylinder is in this configuration, the shortest distance probably is this corner point and some point along this straight line. So these would be the pair of contact points, the closest points, and this would be the shortest distance. I'm gonna call this D minimum. Okay. So the key is to find the shortest distance. Okay. However, in some configurations, for example, this is a different example. Now the obstacle probably is here. In this case, you are trying to find the projecting point here and the closest point there. In this case, this will be in the D minimum. Okay? So from here you can tell you still need to figure out a way to find the pair of points that indicates that shows you the shortest distance. Still, it's a kind of optimization process. But we realize we don't really need to, it's a geometrical problem. It's not yet optimization. So one good way to study this is to assign some kind of coordinate system. If I choose the middle point of the cylinder and then I say this is a coordinate called radius, R, indicate radius. So this is radius. Basically, radial direction. Radial direction. Okay? And going up, I'm using, what was the coordinate I used? I think I used L. Did I? I need to check I have a PowerPoint. Let me see what I use. I use L. I use L. Okay? Okay, so this is L, and basically this is the axial direction. You know, it's really hard to pronounce AX like that. In USA, whenever I pronounce it, people laugh. No Taiwanese is here. No one get the joke. Doesn't sound right. Okay. I'm videotaping myself. I better not talk about that. Anyway, it's a very hard word to pronounce. So let's say I have this coordinate, and I have basically the radial direction could be anywhere. I just need to find the radial direction that is pointing at the plane where I see the obstacle. So in fact, if I draw this more precisely, you are having a plane I don't know, my hands are super conductive today. I can release my hands on the pen. So here's the, come on. Don't touch it. Yeah, let me use the book to protect. Now then, okay, this is the L direction, and this is the R direction. And let's say the obstacle is on top. On top of the RL plane. So this is the obstacle, and let me choose a symbol Q as the obstacle. So in this case, I have some value R here and some value L here. Okay, so you can say the relationship between the obstacle and the cylinder could be described by this RL coordinate. Okay, and I'm gonna define the radius of the cylinder as, I think, capital R, and the total height as capital L. And I need to describe, let me double check what did I use. Oh, I use R symbol. Yeah, that's right. So, since I said we have multiple joints, and that means we have multiple parts. So let's call this is the J simplified cylindrical model. So in fact, your robot arm will be looking like this. One cylinder, the other one probably looking like this, the third one probably looking like this, another one. So there will be multiple cylinders. And they will be overlapping with each other. It's okay to overlap. Because you are basically having a spherical obstacle, you are trying to compute the shortest distance between this guy with this guy, this guy with this guy. You're computing that. You have the d minimum. So let's say this is the j equals to 1, j equals to 2, 3, 4, and 5. So you can call this d minimum 5. This one is d minimum 2. You will have 6 shortest distance between the spherical obstacle and the cylindrical part. You can have 6 of them. So among all these 6 shortest distance, the overall minimum one is the true shortest distance between the obstacle and the entire arm. Okay?
So I need to find this. The D, come on, my arm. So D, let me call this a D minimum. Just put a star right here, okay? The star represents the overall minimum equals to the minimum of the minimum, comma, J. J goes from 1 to 6. So the smallest one is my overall shortest distance between the obstacle to the entire mountain. So now what we want to do is to figure out, this is the Jth one. This is the Jth one. So I'm going to call this radius Rj. The radius of the cylinder, I'm going to call this Rj. And for the spherical obstacle, I'm going to call this R0. Okay? And then we are trying to determine this D minimum, comma J. Okay? We're doing that. So how do we do that? We can then view this whole thing into another planar way. This is the radius, this is the axial direction, and I can draw something like this. This is basically Rj. This is half of capital L. Right? So what I'm drawing right now is this area. Can you tell? Okay. Can you tell? Okay. I'm drawing this pink rectangle. That's basically the pink area on the top in the 3D drawing. Okay. So the obstacle could be somewhere here. That's my Q point. Okay, or anywhere. Now I have to divide this whole space into multiple regions, and I will tell you why. Now I'm gonna draw some straight line here. Distance right here is R0. This is R0. And here is like a quarter of a circle. Okay? So when my Q point, let me keep on drawing. Let me just draw this straight, like lengthened. If my Q point is in this region, if my Q point is there, then how do I compute the shortest distance? It's gonna be this. Right? It's gonna be that. And actually, because the Q has a, let's forget about the radius of the obstacle for now. Later on, we just need to be aware, okay, the obstacle has a radius. For now, we just consider its center point. So the shortest distance between this particular point and this is like the cylinder, right? It's going to be the red arrow I have drawn. So what you need to do is, if one day you realize your Q point is within certain region, that distance can be computed like this. Okay, so what is that called? So I'm gonna call this region. Do I use the same symbol? I think so. Let me call this region 1. Okay. This is also 1. So inside region 1, the shortest distance, d min, will be the L coordinate of Q minus a half of capital L, right? So it's gonna be coordinate of L minus a half of L. Why? This is L, this is half of L, so this is small l minus half of capital L, right? So from here you can tell, whenever I know the coordinate of the obstacle, and at certain configuration for the ith part of my body, I reduce it into a cylinder, simplify it as a cylinder, and then, of course, based on kinematics, I know what the cylinder is located and oriented. Compared to the Q coordinate, I will instantly know what would be the R and L coordinate for the ith part. And then I determine where is the coordinate of Q. If it's inside the region of I, the shortest distance is L minus big L over 2. It can be easily computed. So if, in another case, if this is region 2, then maybe this is also region 2, what would be the best way to compute the shortest distance? You can choose the corner point. It's going to be like that, right? If it's inside the entire region 2, the shortest distance is going to be the center of the sphere and also to the corner of that rectangle. So how do you compute that? Basically, you need to figure out what is this, and then what is this, right? So in the region 2, d minimum is going to be square root of r minus rj squared plus L minus half of capital L squared. Right? Similarly, if you are in region 3, the obstacle, for example, is here, then the shortest distance is here. In region 3, d minimum is gonna be r over rj. That's it. Right? How about region 4? If your obstacle is inside region 4, your robot is ruined already. Right? But when you are trying to plan the motion, you are planning it with simulations. Before you truly ask the robot to move, you need to complete all the calculations. Since you are doing calculation, then it's possible while you are, it's like you are estimating. So without the cut, at some moment, your robot could be having this configuration. And since the cup is going to be here, you see some part of my arm could be overlapping with the obstacle. So in fact, when you are doing calculation, region 4 is possible. But how do you compute the shortest distance if the obstacle is like inside the particle? At least give a value. Okay? So in my research, I think I used the shortest distance away from the central axis. I think I used it. You can have different opinion and you can evaluate in a different way. This is not the exact way to do it. This is still a really open research direction. Some researchers do it in this way, some researchers do it in a different way. It's as long as it works, it's a good algorithm. So I'm teaching you what I believe, or what I use. So if the obstacle is inside the body, I think you can use the distance away from the central axis. It's like how far away the obstacle is away from the central axis. That's what I think that's what I used. So in region 4, I think the minimum I used was off. I think that's what I used. So you keep on evaluating. It's like at the beginning. Let's say you are doing this. You are moving from P0 to Pn, and you need to check every intermediate configuration. If you are moving straight, then you need to perform inverse kinematics for every intermediate point. And for every intermediate configuration, you determine the shortest distance between the obstacle and that configuration. Okay? So let me write down a procedure, like a general procedure. So the procedure was to move from A to B with awareness of collision with obstacles. Oh, by the way, if you have no idea what is this is with, and this is without. This is because. Okay? I'm not kidding. In USA, no professor writes the whole world. This is like this. And what is WRT? Who knows what is WRT? With respect to. What else? I think those are the most commonly used when they write down the notes. Okay, so what's the general procedure? First, you have given P0 and Pn. Okay. Second. Hello. If you are moving straight, then you need to figure out P1 to Pn minus 1. Okay? And then you need to do inverse kinematics for x1 to x n minus 1. That's for the case if you are moving straight. If you are not moving straight, if you are, so I use a 2-prong. If you are just having a curved trajectory, then you can directly do inverse kinematics of P0 and Pn. So you will get x0 and xn, right? Then you can compute for x1 to xn minus 1. So you can linearly change the angles. Okay, so either way, step 2. For the step 2, you need to figure out the configurations along n minus 1 configurations. Next, of course, you need to know the obstacle. So you need given q. Q is obstacle, right? Given q. Now, you need to do some kind like a for loop. So for each ith configuration, conf means configuration. So first time, so I'm just configure. Conf is configuration. Okay? So for the ith configuration, so in computer you need to do a for loop because you need to check every configuration. For the ith one, you need to do basically another for loop for basically each of them. The jth body, we already simplified the body into cylinders. Okay? You need to evaluate the minimum distance between the jth body and the obstacle q. You do all of them. So imagine how many calculations you need to do. That's why we don't want this D calculation to be too complex. This is already a pretty simplified way to do it. But actually this requires some kind of coordinate transformation. Because when you are studying this, you need to figure out the center point of the jth body part and what is R, what is L. It also takes some time. You need some kind of transformation. So this evaluation of D minimum is not very straightforward. So what's inside this, there are smaller steps. You need to, let's say you are focusing on the jth body part, so you need to transform your calculation to the R and L coordinate for the jth body at ith configuration. Yeah, as you can tell, it's a lot of them, right? And then in the RL coordinate, you need to figure out what is the RL of your obstacle Q. Because this is my body part, right? Usually you have your analysis in the world coordinate. Everything, the world coordinate doesn't change. However, when you are studying for obstacle avoidance, you need to study on the body fixed frame. So no matter where your robot arm is, and you're studying for, this is the Jth body part, you are studying on this body fixed frame. So you need to know how to transform from the wall coordinate to this body fixed frame by forward kinematics, because you know at this configuration, you know all the joint angle, you know the geometry, you should be able to find out what is the body fixed frame on the Jth body at the ith configuration. Once I have this, I need to figure out in this coordinate, what is my coordinate of the obstacle, Q. So that's another coordinate, because another transformation, because the Q was analyzing the wall coordinate, not on the body fixed frame. So once you are able to transform the wall coordinate to the body fixed frame, you should be able to figure out what's the Q point in this body fixed frame. Okay, that's the tricky part. Now once you have it, then from what I show you here, you can easily determine what is the shortest distance between the obstacle and the cylinder. And there are 4 different regions using 4 different equations. Okay? So once you have that, then you can compute for the minimum. And you basically do this repeatedly for every frame, every configuration, and for every body part. Then you will figure out then you know you will get the D minimum with the star. I call this the overall shortest distance for every configuration, because you will, from the for loop, you will get every shortest distance. And for the ith configuration, the overall D minimum star is gonna be the smallest one between from the shortest distance between the obstacle and every part. You have a minimum distance 1, minimum distance 2, minimum distance 3. You have 6 of them. The smallest one basically is the shortest distance between the obstacle and that particular configuration. You have n-1 configuration. So for every configuration, you know what is the shortest distance between that particular configuration and the obstacle. What to do next? You set up some kind of threshold. How close you can allow. So let me just a brief. So for example, just one example. Let's say again, this is time, and this is the start, and this is the end. And let's say I have so-called a curved trajectory. So my joint angles linearly changed from the start to the end. So let's say this is my theta 1, maybe my theta 2 is here. Just a random example. Maybe theta 3 is here. Let me just draw 3 of them. And maybe at the end, I need to change my joint angle in such a way. Okay? So I perform some kind of movement from a starting configuration to a final configuration. Okay? And within this trajectory, I studied everywhere, and this is like the J, not J, I configuration. I studied the ith configuration. And I realized at this configuration, some particular configuration, and the shortest distance is some value. So maybe the shortest distance is this value. And I keep on doing this, I realize the shortest distance could be something like this. Okay? If I did all the calculation for every ith configuration, and I actually being able to draw a curve like this. And maybe, by the way, this is shortest distance. Different unit. Blue one is angle, red one is distance. Maybe there is one allowable shortest distance. So maybe, let me use a different color. Maybe this is the allowable shortest distance. If that's the case, that means within this region, I need obstacle avoidance. So the key of doing obstacle avoidance is that you need to figure out along every moving trajectory at which portion you need to change your coordinate. So always figure out what is the shortest distance between the obstacle and the robot. Okay? Now there are so many different ways to find the newer trajectory so that your robot can move around the obstacle. There are so many ways. Later on, I have a PowerPoint. I want to show you how everyone is doing. I think now is a good time for me, for us, to take a short break. Okay? We didn't start until we didn't start for 17 minutes already. So I guess everyone took a lot from today. So let's take a 10-minute break. Later on, I will not do a break. I will keep going. I will go through my slide, and I hope I can finish my slide today. Okay? So let's take a break. I think we can continue. I know one of your group still need to do the case study, so I will try to finish within before 11:30. So there will be some more time for the group to present. Now I will switch to the PowerPoint. So I gave this presentation in a very interesting country called Latvia. So if you have no idea what is Latvia, Latvia. So that was my first time to Latvia because I have an international project with them, and also with Lithuania. What is Lithuania? Litauen. So it's a 3-country project. So when I first went there, I was invited as a keynote speaker. I need to tell them where Taiwan is, otherwise they think we're Thailand. So that's what I did. And I think for you guys, you can use this opportunity to know where it is Latvia. So Taiwan is like size-wise, is around half of Latvia. What's interesting about Latvia is that they have no mountains. They have flat grounds, a lot of forests, no mountain. So our Latvian partners came to Taiwan this year as well after the COVID. They were so excited about mountains. They have never seen mountains for their life. So I think some of our partners went to the Elephant Mountain one day just to experience mountain climbing. For us, it's boring, right? Anyway, population-wise, Taiwan is 12 times larger than Latvia. We have 23 million, they only have 2 million. Taipei is 2.6 million. Taipei itself is having more people than entire Latvia. And I told them Taiwan is not Thailand. And by the way, anyone is from China? No? Okay, I told them we have a fuzzy relationship with China. I told them about there's an election and then it's crazy. Anyway, starting my talk. I started my talk with this video. Let me tell you what this video is about. So it's an it's a National Science and Technology Council project. So in this project, we are supposed to, this is a student from Professor Cao Longyang in industry management. So we don't like to have boys as a model, beautiful students. And the robot is picking up something, and the robot is supposed to drop the part in front of the student. And she intentionally moved her arm to a certain spot so that there could be collision. And from this video, you can tell the robot made a route surrounding the student's hand. Because when it realized there is an obstacle, the student's arm was considered as the obstacle. When it realized that there is an obstacle, some calculation was done inside the computer, and then asked the robot to stop and move along a different trajectory. For the rest, it's just the other part of the project. Our partner analyzed human motion and realized what is the right moment for the robot to join this collaboration. But actually, to make sure this operation moves smoothly, we put some buttons here. Actually, we push the button so the robot knows when to come. But eventually, we don't want the buttons. We want this to be done with some kind of agreement. Whenever the human complete a task, computer should know the robot will jump in and do the next move. But right now it's very challenging. Anyway, let's see the obstacle avoidance again. So I will tell you when the robot realized there's an obstacle and then decided to move around the student's hand. When she moved her arm forward, looked closely, the robot stopped for a very short time and then took a new route. Within that short period of time, all the calculations were done. So look carefully. Stopped. Right there it stopped. And then took a new route. It was not a smooth movement right there because you realized, oh, there's some obstacle. Okay? Like I said, Within this research, there are 3 parts. The first part was done by myself and my students. We work on path planning with obstacle avoidance. The other part was done by Professor Yang Caorong in industrial management. He used a camera to realize what the student is doing with human motion recognition. The third part is laser projection. This is by Zhang Jingyuan from Taipei Tech. He made one laser at the top. There is actually some laser indicating what the human worker needs to do, like a hint. But it was not clear in the video. If you are close by, you can see the laser. So anyway, this is what we have done. Later on, when you work on the project, if you are interested in this kind of topic, you can let me know. I can find my graduate student to jump in and then maybe show you what's available and what you can work on. So this is actually the exact procedure that I showed you earlier by the hand return procedure, but this is more like a block diagram. So whenever you have a plan for motion, let's say moving from P0 to Pn, you need to detect whether there is obstacle. So usually you have some sensor or camera surrounding the working environment, like what I showed you in the video. There's actually a 3D camera recognizing the 3D coordinate of the student's arm. When the arm comes in, all the coordinates were captured and tell the system that along the trajectory there is this particular obstacle. So our system was basically doing exact calculation that I showed you. And once we compute every future configuration, because if you move up to a certain point, you don't need to worry about what's in the past. You just need to worry about what's in the future. So over here, the computer is calculating every possible configuration in the future and the shortest distance between the configuration and the obstacle to check whether it's safe. If yes, continue. If no, you need to use something to replace the trajectory. And this is exactly what I told you about the simplified model. Every body part has been simplified as a larger, fatter cylinder. It's easier for distance calculation. So in this animation, you probably can understand what this procedure is about even better. So from P0 to Pn, originally it was supposed to move in this way. However, while it's moving, there is an obstacle being detected. Then we check it's not safe. We realize within a certain region, every configuration within this region is not safe. So we choose this region as a obstacle avoidance region. We need to move. We need to find a safer route. So in this research, we need to find this new trajectory so that our robot can move like this. Okay? So let me tell you what people have done in this field. There is one way, so-called the potential field method. All kinds of potential field. Basically, this algorithm not only can be used for robot planning, can also be used for like a vehicle positioning. Okay, it's very commonly used with this potential field method. Of course, the assumption is you need to know where are the obstacles. Those are obstacles. Then you have a starting point. You have actually the starting point here. You have an end point. So you know all the coordinates. Now, most straightforward movement is to move straight, right? And as you can see, along this straight line, there's gonna be collision. So in computer, when we try to do this, we already know there is collision. And since we know about the coordinate of everything, they assign some kind of potential energy on those geometries. So they're like magnets. They have opposite magnetic field, magnetic force, pushing you away from the wall. So when you are about to move up to here, that magnetic field pushing you toward the other direction. So over here, computer figure out some kind of algorithm to realize you have to move along a different way. So not only they have this negative that potential field pushing you away, they also have some kind of magnet from the target. So the magnet is pulling the starting point toward itself. So this is like a positive potential field, and the obstacle are like negative potential field. This pushes you away, the target pull you in. With the combination of all those magnetic fields, it determines where to make the turns. Okay? The issue of this method is that think about all these possible positions in the design space. Whenever you need to figure out where to make turns, in fact, you need to compute the shortest distance. The potential field, every potential field is computed based on that shortest distance. If you are closer to the obstacle, the magnetic field is going to be stronger. So if you move even closer, that you have even stronger potential field. So all these calculations is basically based on the shortest distance calculation. So since this method is exploring the entire design space, you can tell they have small arrows in our magnetic fields. They basically study everywhere inside the space, and then they can freely move without collision. But that requires a lot of calculation. So a different way is called the Dijkstra algorithm. The Dijkstra algorithm doesn't require you to move along the entire design space. It's a floor exploring algorithm. It's like pouring water from the entrance, and then the water started to explore until the water reaches, it's like flooding, reaches to the target. Once it reaches the target, the computer will figure out, okay, how many steps it has been taken. There is one trajectory or multiple trajectories that took the shortest path, then move along that path. Okay? The issue of this, what's the issue of this? Whenever you explore, again, you are checking every position, whether that position is safe or not. Whenever you are checking if it's safe or not, you are checking the shortest distance. So from here, every red point requires one time of shortest distance measurement. That's also allowed. The next method is called the A-star. It's an improved Dijkstra method. So in A-star, they don't try to explore everywhere. So whenever they take a move, in this 2D space, you basically move forward or move left. They have some calculation to decide, okay, is forward better or left better? They will decide one. So they always move along one direction. Until up to here, moving this direction makes more sense because it's closer toward the target. But whenever it's bumping into an obstacle, then you need to explore more. You see, over here it's actually exploring more, some extra exploring. here is more like an A star, like a Dextra. But it doesn't overdo it. You only explore the space close to the possible path. And again, even you're doing this, you are still checking shortest distance. Okay. Now this is, from here, people started to try different ways. They try to use random procedure. So this is so-called a probable roadmap, probabilistic roadmap. What did they do? They basically assign random intermediate points in the space, just randomly assign them, and then try to connect the dots between. They try to connect the dots with straight lines. They don't connect the long ones. They just try to find the closer ones surrounding every point, and then try to connect them. They don't connect the long ones. So whenever they connect those straight lines, they start to determine whether on a specific line collision is going to happen. So over here at the bottom, that yellow point is not a good point because that caused collision. So that one will be removed. Once you have some kind of network that allows you to have a connection between the starting point and the end point with zero collision, then pick up the shortest distance. That's it. However, when you have that, the checking whether it's collision, you basically have distance measurement. Okay. So if you need to do distance measurement along this path, that means you need to do that everywhere. On every connection, you need to do distance measurement. Still, it's a lot of calculation. Okay. So someone come up with this newer, more advanced approach, so-called RRT, Rapid Exploring Random Tree. This method, the two most famous methods in path planning are A star and RRT. A star is easy, RRT, the procedure is more complex, but it's quite efficient. So they don't explore the entire space anymore. They start from the starting point, just explore your neighborhood. If there is a bad path, eliminate the bad one. Okay? And then you don't pick up the one that's over a certain limit. Like earlier, this one collides, even if it's inside a certain allowable region, but it collides with the obstacle. This one is eliminated. This one is outside. You don't want that. You just want to explore the neighborhood. So keep on doing that. You could have small branches until you reach to a certain area where a point is close to the target, within a certain range. Then you connect the target with the end of the branch. So you find a trajectory, a complete trajectory. So researchers believe with this way, you don't need to explore too large a space. You just we can go through a smart trajectory. Then there's someone tried this dual tree RT. Same idea, but they have two branches starting from both the starting point and the end point, like this. Okay, until both branches have single point closer to the other one, then they connect those two neighboring points so that they find a complete trajectory. They believe this dual tree RT allows you to explore lesser space. You don't want to explore the whole world, right? You just want to explore what's possible. Okay, now I would like to introduce what we did in our lab. There's a reason why we don't use A star or RT. A star is more like an exploring algorithm. It's like you don't need intelligence. You just need to explore. You just find a more effective way of exploring. And for the RT, it's based on random process. My research field is about optimization. We don't like random process. My advisor and my advisor's advisor, we never use random. We don't like to use random points. We would like to derive algorithms that helps you to find a solution. So if you want to know more about what I'm planning to do, you need to take my optimization course. If you have done, basically the difference is there is a bunch of algorithms that's based on so-called gradient. The other ones are based on random process. We don't use random process. Only the weak students use random process, like a genetic algorithm. When you publish a paper, if you use genetic algorithm, the other group of people will think, nothing smart. So we want to develop something that's smarter. Okay, so in general, you are moving from, this is basically the P0 and that's the Pn. And it's a general configuration, so I use, the robot can have any shapes. So it's a general configuration. This is a J's body, right, like I said. And this is the coordinate of the any vector. X is representing the joints, the vector of joints. Okay? Basically the configuration. So let's say there's an obstacle Q on the way. At a certain moment when your robot configuration is having the first contact, I'm calling this the first collision point. So F represents first collision. And the robot keeps moving until it reaches to certain configuration like this. And if this is the last configuration that has collision, the next moment it moves, the collision finishes. So I have a first point and a last point. So that I define this as a robot collision region. We want to avoid this part. However, if I move my robot up to here and start to make turns, you already have tangent contact. You don't want that. So in our research, we usually find a configuration a little bit earlier away from the collision. Because we already use first and last, so over here we use head and tail. So this is the head point to avoid the collision. And then we find a tail point. This is the tail point, head and tail. So we define this region as the obstacle avoidance region. If we are able to find a trajectory that will not, that is away from the danger region, so we won't have contact, and also we can move around it. So let's focus on this collision avoidance region. Over here, we pick up some intermediate point here, some intermediate configuration. The idea is that we basically want to find a newer configuration from here to here. So here is not safe, here is safe. If you can choose multiple points here, then you can find multiple newer configuration on above it. Then you can just connect them. So that was the idea. We focus on one configuration and find the safer one to replace it. Okay? So that's the goal. If you can find one, then you can find a lot of them, just connect them later on. So from now on, we are going to focus on just one configuration within this obstacle avoidance region. Now, here's the trick. We don't want to deal with end effector coordinate anymore. From now on, when I do any analysis or optimization, I stick with the configuration coordinate, basically a vector of joints. Why do I do that? Because I don't want to do kinematics anymore. If I use the end effector coordinate right here, then in the later analysis, I need to do inverse kinematics for x and then forward kinematics for p. I will need to do this back and forth for so many times. I don't want to do that. That is wasting some time. So let's focus on the design coordinate with x. If it works, I never need to do kinematics anymore. So the idea is I need to find a newer point right here to replace this one. But this one was a good one. The only bad thing about this one is that it will collide with the obstacle. The main reason is because it's not safe. But this particular point fulfill your objective, which is moving from the left to the right. So that was a good point. So the idea was I try to find a point that is as close as possible to this original point. I want to be closer to it because this was a good one. So I set up an equation that calculates the distance between two. Okay? Remember that I want this to be small. It's okay to be small, but when I try to make this smaller, I want to keep my safety. So maybe when I reduce the distance up to here, it's already reaching my safety level. Then I don't shrink this distance anymore. Then I will be finding a safe point that is the closest to my original. So I will be moving just surrounding the obstacle, not like this. I don't want to do this. This is a solution, of course, but it's less efficient. You need to move with a longer time, waste a lot of energy. You want to do this, right? Just enough safety. This is too safe. Okay, now, that is one. And we realize we also need to shorten this distance and this distance just to balance, make a good balance. These ways are very similar to the potential field method. They are like magnets. They have pulling forces. If I try to shrink all three directions, this point will be pulled down toward the original. Okay? So that was the idea. And basically, that's a lot of math, so don't worry about some of the math. Basically, over here, that's where it's dangerous. So we want to evaluate something called the danger factor. The danger factor is going to be calculated by the shortest distance. I want the danger factor to be small enough. If it's too high, we believe it's dangerous. So I will tell you about the danger factor. So exact analysis that I did, but this time I choose to use so-called danger factor. There's a reason. Because robots may have large ones or small ones. For large ones, maybe you are in a different scale. The larger ones could be 2 meters tall. Small one could be 50 centimeters tall. So when I apply the general method to robots with different shapes, I want a unified unit. I don't want the analysis to be affected by the size. So usually when this situation happens, sometimes we would like to normalize our values. We choose to define a new value called danger factor. Whenever the obstacle is right on top of the center axis of the cylinder, we say this is 100% dangerous. So danger factor equals to 1. Whenever the obstacle has tangent contact with the cylinder, even it's like this, or corner points, or on the side, whenever it's like a point connection, we say this is 50% dangerous. When it's away, 0 dangerous. So if we can model this danger level with values from 0 to 1, it's a unified no unit. It's just a percentage. So basically, exact same calculation, but over here we need to cut into 6 regions, unlike what I showed you earlier. Because we did some math to realize the danger factors has to be written in certain equations. It's more complex than the one I showed you. The handwritten one is a simplified version. This is a more because of the danger factor. Okay, so what's this? That's how the danger factor changes when the coordinate of the obstacle changes its coordinate. So I would like to show you what this means. So this is the exact drawing. If the center of obstacle is on this red line, danger factor has to be 1, right? So pay attention on the coordinates, the L. L is the axial direction of the cylinder. So L in this figure is right here. So here is L. So this edge is representing this red line. Okay, up to one half of LJ. This is 1/2 of LJ, right? Up to here, within this range. And R equals to 0. This is R equals to 0. So over here, this is like the obstacle staying on the central axis. And like I said, I want this danger factor to be 1. So these are danger factor equals to 1. Okay? And when the obstacle center is staying on top of the red dashed line, we will have point connection with the cylinder. So over here, I need a danger factor to be 0.5. This red dash trajectory is shown here. And take a look, it's 0.5. Okay? Now, when it's far away, I want the danger factor to be 0. And as you can see, when it's far away, it's 0. So we designed this danger factor within 6 different regions with those equations. So we try to make this danger factor as a smooth function. But it's not completely smooth because we have some corners right here. It's not good for derivative, I know, but it works okay. At least this function is well defined everywhere. So no matter your obstacle is inside the design space, no matter where your robot configuration is, you can find the RL coordinate of the obstacle and the J cylinder, and then plug in one of the equations, then you know the danger factor. Okay, that's what was done. And then it's about optimization. So if you haven't taken my optimization, this is for your future. Take my optimization, then you know how to do it. So we want to minimize this distance, minimize this, and minimize this. ST means subject to. Subject to means 受限. So basically limited by. Minimize these 3 things, but limited by those equations. One limitation, one constraint is your danger factor has to be smaller than an allowable value. If it's greater than 0.5, collision happens. You can set up as 0.4, so you will be keeping a safe distance away from the cylinder, because 0.5 is like a point contact. 0.4 is a little bit far away. So usually we use 0.4. And your angle, joint angle is limited by its largest angle and the smallest angle. Okay, and like I said, we formulate 3 equations. We want them serve like magnets, pull the design point closer to the original one, but keeping the safety value. So formulation-wise, I believe you can easily understand, but mathematically, you may not be able to understand. I'm going to show you, but don't worry. You just do not worry. There is something called Lagrangian. This is solely the auxiliary function. This is a constraint function. This is actually one constraint function, the other one constraint functions. This is called a constrained optimization. It's difficult to solve for constraint optimization. It's easier to solve for unconstrained optimization. So there's one way to put constrained functions together with the auxiliary function. It's so-called the Lagrangian. So it's like a weighted sum. Sum them up with some weights. Some weights. Those weights, 权重, are called the Lagrangian multiplier. You may heard of Lagrangian multiplier. What are they? They are the weights, 权重, in front of the constraint functions. So you just need to put them in the constraint with some weights. Okay? So this formulation is called the Lagrangian. But it's not easy to directly put that in the auxiliary function. When you try to take a look at this, d minus d bar, forget about this, must be smaller than 0, right? But when you want to put this in Lagrangian, you need this to equals to 0. Cannot be smaller than or equals to. So we introduce a new variable. S squared is always positive or 0. So if this whole thing equals to 0, this value is either 0 or smaller than 0, right? So if this is 0 or smaller than 0, it's equivalent to its original equation. So we introduce something like this to make this equation equals to 0. This is only how you can put into a function. Whatever you put right here are called the slack variables. Slack variables. Okay, I don't know why they do this. They're just names. Okay. If you don't know this, it's fine. I can give you the slides, but you can try. Once you have single auxiliary function like this, then there is a famous method called Newton's method. Newton's method helps you to find the minimum. Okay? Whatever Newton's method you have learned probably is to find the root. 求根, like function, finding the root of the function, right? Usually Newton's method tells you where you have f equals to 0, right? But in optimization, we try to find where the derivative equals to 0. So Newton's method in your high school or undergrad teaches you how to find the root. But in optimization, it teaches you how to find the extreme point. And in our case, we're finding the minimum point. And it's a mess. This is so-called gradient vector. Gradient vector, yes. This is the Hessian matrix. The gradient vector looks like this. Okay, if you're interested, you can take my optimization. And I'm gonna show you the Hessian. Looks like this. And so, just math, okay. Anyway, we can solve it. So the entire procedure looks like this. You want to move from A to B. You determine all the coordinates during the trajectory, during the path. You determine all the configurations. You check whether it's colliding. How do you check? You plug into the danger factor that we developed for every possible configuration. If yes, there's gonna be collision. Determine what is the first collision point and what is the last one. Then move wider, choose a head point and a tail point. That's where you want to do obstacle avoidance. Within this range, choose several more intermediate points. Solve for the optimization that I just showed you. And then you will have newer points connected. Then that's the avoiding trajectory. Now, time for animation. So here's one robot, and the red box is an obstacle. So originally, it is supposed to move like this, okay? From right to left. Along this path, this is the joint angle. I have drawn these figures for you earlier. Take a look. We have six joint angles. At the first point right there, the 6 axes are shown right here, different angles. Along the path, it's gonna move like these. Some are straight lines, some change a little bit, and some even move like a curve. Because when my student did it, I think he chose to move along a straight line. So if the end effector is moving along a straight line, you know the angle is gonna change like curves. However, we evaluate the danger factor. The red dashed line is the level of 0.5. As you know, 0.5 is collision. So the danger factor up to here becomes greater than 0.5, and then it's gonna collide, just like how we evaluated right there. So if we take a look at all intermediate points, we chose 3 of them. Now we want to perform optimization to find better intermediate points. So this is where we want to avoid. So focus on the first point. We use the optimization, Lagrangian formulation, Newton's method. During optimization, usually it's an iterative process. Iterative. So the solution is gonna be moving around until you find a good one. So I'm gonna show you the iteration. First iteration, second, third. Oh, that's optimal. We found an optimal, a good solution right here, which is close to the original one, but keeping a safe distance. Okay? Let's take a look at the second intermediate point. Over here, it was colliding with the obstacle with optimization. First iteration, second, third, optimal. So we found the optimal solution right here. Again, close to the original, keeping a safe distance. Okay. The third intermediate, first iteration, second, third, optimal. Okay, so that was purely done by math. We have no idea how. Basically, mathematically, Newton's method proved. If you have that formulation, this is the solution. Okay? So overall, this was the original path. This is the newer path. So in fact, it moves like this. Just like how human would like to avoid the obstacle. And I'm showing you the dashed lines. The dashed lines are the improved ones. Over here, like this particular joint, black one is the 6th joint. It has to move along a new trajectory. And all these determined by Newton's method. And like the blue one is the 3rd angle. It has to move like some new trajectory and determined by the algorithm. With the newer combination of the configuration, check out our danger factor. It's within 0.4. It has no chance to collide. Okay? And I'm showing you one animation. So the top one is basically exact problem that I showed you in the previous slide. The bottom video is a different path. So originally it is supposed to move from top straight down, but there's collision, so it made avoidance from the side. Okay, so this is with the first brand of robot. We did the same thing for a second brand of robot. Basically, this method is general enough. No matter what brand of robot you're using, it works. Okay, you just need to update the geometrical information. Okay. This is an interesting project. We work on an 8 degree of freedom robot. So usually a robot arm has 6 degree of freedom, but this one has 8. We have a slider on this arm and this arm. So this robot is allowed to lengthen itself and then shorten itself. Why did the company do that? Because sometimes they have something in the shell, they want to pick it up, but the length of the robot is not long enough. So sometimes they need to lengthen it. But they don't want the robot to be long all the time because the walking space becomes too far away. Sometimes you cannot reach somewhere closer. So with the ability to change the length, sometimes you can reach closer, sometimes you can reach further. But when they design this, as you can see, you have greater degree of freedom. Now you have 8. You only need 6 degree of freedom. So you have 2 extra degree of freedom. So your possible solution become infinity. You have an infinite number of solutions for inverse kinetics. So usually for this kind of redundant degree of freedom robots, to find the possible configuration is more troublesome than 6 degree of freedom robot. Anyway, so what happened when we worked with them? They wanted to move from a point to a new point right there, and the joint 3 and joint 5 in this case, not 3 and 5. I think it's 3 and 1. I don't remember which one. Yes, 3 and 5. The joint 3 and 5 never changed. It's within this 0 area. So it moves just like a 6 degree of freedom robot. It never tries to lengthen itself. So from here you can tell, along the path, the danger factor reaches to very high. Some part of the body pass through the center of the box. So it's reaching close to 1. So we want to avoid those. Similarly, we use optimization to find a better point. And our method is general enough. We don't even care how many degrees of freedom we have. We're still being able to do this. So for iteration, first, second, third, fourth, fifth, sixth, seventh, optimal. So this is optimal. Second configuration, first iteration, second iteration, third. Okay, this is a fourth, optimal. Third configuration, first iteration, Oh, that was nothing else. So the third configuration finds the optimal more quickly. So overall, it's moving like this. Combined together, this is the original trajectory, this is a newer trajectory. So what's interesting about this is that originally joint 3 and 5 doesn't change its length. This particular pink one is joint 5, basically one of the arm. The optimization asks this joint to change its length because it helps you to move around the object. So our optimization has no problem to modify the length. And the safety factor was kept within 0.4. This is another video to finalize what we did. So let's enjoy the video together. Exact execution that I showed you at the beginning. So that was the laser that I mentioned. So the laser is pointing at the position for screw. So maybe you have a mechanical part that is large, have so many screw holes, then the laser can help the worker to realize, okay, put the screw here and there. And that was the human body frame recognition. That's it for my presentation today. So I will share what I have, my slide on PowerPoint, on iPad, and also the PowerPoint I have. But I will remove the one with a degree of freedom because I'm not allowed to put it on YouTube. I'm not supposed to. Okay. Any questions so far? Do I need to assign homework? Do I need to assign homework? No. Not for this one. Right? Do they need to write something about today's lecture? Up to me? Okay. Do you want to try to study path plan? But not the difficult ones. Try the simple ones. For example, this one. You know, this is done by Meta, and this could be done by Meta. If you have just consider a 2D space. If you have a starting point and an end point, and you have some obstacle, you can have simpler obstacle like a circle. So if the circle is on the way, you are defining your intermediate point, you realize, oh, your end effector is too close to the circle, you can try to find a newer path. So in my slide, we have potential energy approach, Dijkstra, A-star, random tree. They could be quite easily implemented in Meta. If you just stick with a 2D problem, simple circular obstacle, randomly pick starting point and end point. Because whenever a straight line from the start to the end have contact with the circle, how to do. Okay? So I know you guys are in groups, right? Can we have a homework for today's lecture? You guys work in a group and you choose one way you would like and try to implement obstacle avoidance in any way. The goal is whenever, based on whatever assumption or setup you choose, but you need to be able to demonstrate 2D space with some obstacle, circular obstacle with random position, random radius, and random starting and endpoint. Whenever the straight line has contact with the circle, what will be the path surrounding it? And if this has to be done automatically, then it requires some coding. Okay? Work with your team and see if you can implement it. If your team is cannot implement a MATLAB code, you want to try different codes, that's fine. If you just don't know what to do, you just want to, okay, can I just download something from the internet? Okay, that's fine. It's just a homework. But you will learn less if you just took something from the internet. And if you just, okay, even I download something, I have no idea what that code is, it never works, and you just want to study for some method and then give me a report, that's also fine. So I just want the team to focus on path planning, obstacle avoidance as a homework. You choose the level you want to handle. Okay? The best would be, okay, let's focus on RRT, a 2D problem, let's do some coding. Actually, it's not very hard. If you do something like this. Random circle, random starting and end point, put in some random intermediate point, start to connect lines, check each line whether the line is overlapping with the circle. If it is, remove those. So at the end, you will end up with a network without collision. Pick up the shortest path. Nothing too difficult. Right? It could be done within 2 weeks. Maybe 3 days per week. You guys can do it in 2 weeks. So how about handing in whatever you can get within 2 weeks? I don't want this to affect your project, but I think it will be a good start for you it could be guiding you towards something you want to do in the project. In the project, you want more movement, right? And if you want to move, you don't want collision. So if this homework is going to help you on something you want to implement in the project, go ahead and do it. Okay? That's it for me today. Thank you. If you have questions, you can send me emails or talk to my TA. Talk to my student. They will tell the team. They will let me know if you have questions.
Excuse me, Professor. So we have to finish our homework in group, but actually we have 2 types of group, one for case study, one for final project. Which group?
Project group.
Final project.
Work with your project group.
Thank you.
Let me write down the homework so people are not confused. So, homework, work with project group, implement obstacle avoidance with random start and end points. Plus one circular obstacle. Okay, 2 weeks. If you, let's say 2 weeks later, you just want to do it, you just don't have enough time, I can give you 3 weeks. As long as you hand it in to me before the semester, I'm okay with it. Okay. I know if I do this, maybe our scoring needs to change a little bit, but the percentage of scoring remains the same. We just occupy some part of your homework assignment. And I will give your team member the same score. I will not listen to whoever member complains he works more, I work less. I work more, he works less. So I get 10, he get 9. No, you're the same, you're a team. I give you the same score. If someone complains, okay, lesser teamwork, point reduction. So don't complain to me. You're supposed to work as a team. Your final production and how you work together is gonna be evaluated together as a whole. Your team get the same score as the homework assignment. I guess not too many points, just a few points. But I think this will be very interesting homework. Okay. Okay, thank you. I need to give you some time for the case study. I will give you those afterward.
Okay. Classmate. Today we present you on medical robots. Me as medical robot and my friend Lily will go through the presentation. So here is our presentation outline. I will go through on the introduction and structural analysis of some of the medical robots, and my friend will go through the next classifications and applications of, and some important remarks on the medical robots. So to come up with the introduction, medical robots is an interdisciplinary field that focus on developing electromechanical devices for clinical applications. So medical robots simply are robots to assist doctors, nurses, surgeons, and the patients. As any emerging technology, medical robots has their own developmental stages. So in the first stage, medical robots directly adapted from industrial robots and has no autonomy. They were passive. The operator performs all the tasks. This level includes passive and teleoperated systems that are the neuro navigator and teleoperated. The Da Vinci robots were the two best examples. And then after, in the 90s, the robots has emerged or added some developments to assist some technical works for the operators. And they become semi-active, like Renaissance and co-manipulated co-robots. And in the 2000s, the robots has developed to add some autonomy under a close watch of the operator. So the operator maintains discrete control and the robot performs certain tasks autonomously, but initiated by a human. Then after, in the late 2010, the robots add some cognitive autonomy. Operator select and approves the surgical plan. Then after, the robots can do some autonomous tasks. For this, the cyberknife, which is a medical robot used to treat tumors and cancers, and for the some task autonomy, robot for operation work of bones in the leg. And nowadays, for higher autonomy and full autonomy, not yet existing, and they are waiting for researchers. So this is all about the developmental stages of medical robots. So here is some design procedures. There are some important criteria we have to consider during the design of medical robots than some other robots. Safety, sterilization, precision in the positioning of the instrument, efficiency, user-friendliness, and cost are the 6 most important requirements. Out of this, biocompatibility and biomimicry are key considerations for medical robots. And as other robots, it has these procedures. First, we have to make the analysis, and then we have to go for the design. In the design stage, we have to consider the constraints and choices. So we have to make the architectural synthesis and develop the CAD design from the constraints and the choices. And we will make 3D simulations. After having a compromising 3D simulation, numerous prototypes will be developed and will be iterated until we find the best compromise and confirmed by the surgeon. After having this thing completed, we'll make to specify or to specify the robot, like the workspace, degree of freedom, external, internal, and the constraints, force torques, velocity, acceleration, and the like. Next, the structural analysis. Generally, medical robots are designed for specific tasks. Therefore, the number of degree of freedoms, control mechanisms, and the type of structure will be determined by the task to be achieved. So often fixed point constraints for the trocar and the needle will find, and tool row positioning we may find in some OP procedures. Very often tool orientation with spherical workspaces are available, and sometimes tool translation or translation plus rotation can be available. So to be more specific, let's see some of selected architectures in the coming slides. Since most medical robots, serial medical robots are adapted from industrial robots, typically scalar robots, they have 4 degrees of freedom plus possible 1 to 2 degrees of rest freedom. And the workspace is cylindrical, as you can see in the figure, and the workspace will well suited to a patient lying on the operational procedure table. It has less sensitive to gravity and safer in case of power failure because it's already the workspace is cylindrical. The other serial manipulator is a Derma robot from 1998 to 2003. It has a 6 degree of freedom scalar robot with non-spherical wrist. It has a mobile platform. It can move from position to position, and 6 degree of freedom force sensors, laser range finders, and hybrid force and position control. Wrist singularity of the workspace is there. So this robot is typically used for a skin treatment or skin surgery. And the other is the parallel robots These are stiff, accurate, good acceleration, lightweight, load to weight ratio is good compared to serial robots. They are, in fact, they are complex in model. Singularities are less, and we can get small work space with this type of robot designs, and this parallel architecture is common in surgical robots. As you can see in the video, we can just move in every direction. The other important robot is a CyberKnife robot. This robot is used to treat just tumors and cancers with radiation. So a 6 linear photon device is mounted on a KUKA 6 degree of freedom industrial robot. So the overall accuracy of the system is to be 0.42 plus or minus 0.4 millimeters, and the patient's skin motion are detected with a 0.35 millimeter. Infrared cameras to track are used to track the patient's moving body surface, and X-ray cameras are used to track the spatial displacement of the patient and compensate for motion caused by breathing, because since the treatment is with radiation, any small displacement will lead to a huge damage to the patient. So it uses a 4D CT or computer-aided tomography imaging through time to measure respiratory tissue motion. The other most common surgical robot is the Da Vinci, which is developed by Da Vinci Intuitive Surgical. So it has a master-slave system for minimally invasive surgery. It has surgeon's control units, 3-arm surgical robots, and equipped with high-resolution 3D image for the surgeon. It has 9 degrees of freedoms, 6 from the main manipulator and 3 from the surgical instrument. And the current research for this robot is to develop a force feedback. And the other is the CT-guided biopsy procedure setup. It has a 7 degree of freedom robot integrated on a mobile track, 4 degree of freedom for positioning stage, and 3 degree of freedom for position refining stage. And it has 0.66 plus or minus 0.27 millimeter application accuracy. The other, the actuators, as usual, the 3 types of actuators, pneumatic, hydraulic, and electrical type of actuators with their pros and cons can be implemented in medical robots. So each type of actuator has its own advantage and disadvantage. Based on the type of task we would like to perform, we can apply out of these actuators. And about the sensors, there are basically 2 types of sensors, internal sensors and external sensors used in medical robots. The internal sensors to measure the current position during programming and execution of the movement, about the acceleration velocity of the motors inside. Can be analog or digital sensors, maybe relative or absolute sensors, based on the type of task performed. And external sensors, non-contact and contacts. For contacts, we have force and torque sensors, tactile sensors, for non-contact video optical distance sensors, ultrasound, and for inductive and capacitive magnetic sensors will apply to different medical robots. In control, during the control of medical robots, control of positioning movement along the trajectories, synchronization with external events, reading sensor data from the starting appropriate measuring, permanent supervision of the operating data and movement will be transferred just to the controller. In general, for all medical robots, the control commands can be categorized or grouped into 5. Stereo taxic, which the anatomy is rigid or the patient is rigid and the robot moves along a pre-planned trajectory, just like for head and neck in a neurosurgery. And the other type of control mode is image guided with intermittent imaging. The robot adjusts the instrument's position in case of misalignment beyond a fixed threshold. Just example for frameless radiosurgery, and motion compensation or predictive motion compensation for chest and abdomen radiosurgery, virtual wall for orthopedic surgery, and motion prediction replication for urology and cardiac surgery. These are just the 5 groups of control modes for medical robots. The next,
Okay, now I want to introduce application. Besides providing supplies in hospitals, medical robots can also be found in homes and rehabilitation centers. These robots serve different functions in each environment, ensuring that patients receive proper care in various settings. Next, we'll introduce classifications. In the field of medical robotics, there exist numerous types of robots that serve different functions due to device applications scenarios. The following will introduce medical robots in various environments. The first to introduce is the companion robot. In addition to general companionship and conversational functions, companion robots also incorporate features such as measuring blood pressure, blood sugar levels, body temperatures, and medication reminders, catering more closely to the needs of the patients. Next is surgical robots. The use of surgical robots reduces surgeons' physical strain during lengthy postures and offers enhanced precision with an enlarged view of the signal area. However, these robots, while possessing highly precise and stable hands, are not fully autonomous due to concerns about medical reliability and challenge in gathering comprehensive information in the complex operating room environment. Surgical robots primarily aid in minimally invasive surgeries, reducing incisions, minimizing infection risks, and hastening recovery. The following to be introduced is the auxiliary robots. Hospitals face substantial workloads, and robots can assist medical staff in tasks such as moving items, cleaning, restocking, and more. This robot offers high efficiency, flexibility, substantial load bear capacity, and the ability to adapt to various pathways and locations. They reduce the workload on medical staff, allowing them to direct more attention and care towards patients. The next one to be introduced is the escalating robots. Apart from escalator for the legs, there are also escalators designed for arms or fingers, all geared toward assisting patients mobility. These devices are primarily intended for treating stroke patients and individuals with nerve damage, reducing injuries during the rehabilitation period and enabling patients to move more comfortably. That escalator robots feature for prevention mechanism to safeguard patients from secondary injury due to falls. On the other hand, escalator robots offer a linear function that allows patients to use their healthy limb to guide the injured limb through basic movement. Through extensive repetition of movement, this device aids in the recovery of the injured limb. Recently, medical robots play a crucial role in healthcare, contributing to improved medical services, elevated patient care, and the emphasis on human-machine collaboration. However, they encounter technical challenges, notably in safety and pricing. Advancement in machine learning and artificial intelligence hold the potential to address their harmonies, paving the way for the progression of medical robots in the field. This is our review. Thank you.
So I think maybe for this part of it, we can be more specific